It says from the lecture notes, i.e. what we were looking at earlier, but there's also, we recorded what I did earlier. I still need to upload that, but there's also a video there, a previous video, that stuff as well, which you could have looked at if you want to. We know that under the Black-Scholes model with 0 interest rates, and again, I'm just saying, I often assume here just to make questions slightly easier. So there's not some financial reason why I'm setting interest rates here. I mean, although of course interest rates are pretty much 0 at the moment in this era, not like in the 80s when I think they were like 12% or something, but in the UK anyway. So the price of a no-touch option, a no-touch option pays 1 at time t if S does not hit B, which is less than this era before time t, and 0 otherwise. So I should have moved this up here then. So the f function for this particular question is just simply this. Now, the previous example that we were looking at was a knockout European call option, which had a strike and a barrier. This is just simply an option which pays, well, it pays this at expiry, or rather it pays, more precisely, it pays the indicator function of ST greater than B, but only if the stock price has stayed above B throughout the entire time 0 to capital T. So in actual fact, the payoff at expiry is not that, but is rather that, where S with a bar under it is the minimum stock price. So what I'm saying is that the minimum stock price, if I define the minimum stock price at time T to be the minimum of, say, SU for 0 over 0 less than equal to T. Well, okay, actually, usually I'd write that slightly. Yeah, let me write that slightly. Usually, sorry, I'd write that as the minimum. Yeah, I'd usually write this 0 less than equal to U less than equal to T of SU. Then the payoff of the option we're considering here is that. But the F function associated with this question is now simply just whatever the terminal payoff is, which is an S now is a dummy variable if we're just considering the S function, which is just at expiry, the payoff is just S great indicator function on S greater than B, which is written down here, although it probably should really be written up here. So that's weird not doing. Oh yeah, sorry, I forgot I've defined this minimum thing here as well. Yeah, so in case you can't read that, what I've written there is the same as what I've written there. So, so from what we did earlier, well. So I've said that the interest rate is 0, so I don't need it. If I'm pricing this option, I don't need to have a discounting factor outside. So the price of the option is the expectation of the Q of the payoff. There is no e to the minus r blah 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 because the interest rate is 0. Here's the payoff. The payoff, as I've just said, is the indicator function of the minimum stock price over the interval 0 to t. It's 0 to capital T, i.e. this interval is greater than B. If we're considering any time t in this interval, then the price, then we have to condition on essentially the information we have at time t. But essentially for the Black-Scholes model, it's sufficient just to, the only knowledge you actually need is what the stock price is at time t, essentially because of the independent increments of Brownian measure, but I won't go into that right now. So we can rewrite this this indicator function, although I guess we don't actually need this. I don't think we actually need that for the question, but okay, it's an important thing anyway. So the event that the minimum stock price at time capital T exceeds B is the same as the event that the hitting time to the level B is greater than T. That's just kind of common sense, because if the stock price hasn't hit B, it means that the time at which the stock price does hit B must happen after time T. So that's just kind of common sense. Although I don't think, at least in this part of the question, I actually need this HB thing, but I think it comes into play later in the question. But what is relevant from earlier is then that what we saw earlier is that the price of a general barrier option which pays F of ST if more precisely, if the minimum stock price is greater than B, we saw that it was given by this difference of two European options, payoffs. So the original F payoff minus this sort of reflected payoff, if you like, we could call it a shadow payoff. But in this case, the gamma if you remember from earlier, what was it? Half. God, I can't remember. I've got the thing in front of me. Yeah, a half minus r over sigma squared. Okay, but in this case, as I said, we're assuming r is 0 for simplicity. So the power that was here has just become 1. So we can price so from what we did earlier, we can price this particular barrier option in the general way as the expectation of the f payoff minus the expectation, or expectation under Q of the f minus the expectation under Q of a modified payoff, for which the rule is that it's st over b times f of b squared. But in general, remember this was st over b to the power of 2 gamma, but gamma happens to be 1 because I'm assuming that the interest rate is 0. Then but what can we say here? Well, but in this particular question, the f, as I've said, is just this indicator function of s greater than b. So that's just what I've written there. Similarly, yeah, when we evaluate this f of b squared over st for this particular f, if we just do that slowly, then, or maybe we can do it over here. So it's the indicator. I mean, the original function is s greater than b, but now because we're being told to plug b squared over st, it's indicator b squared over st greater than b. But then you can rewrite that as the indicator of b greater than st, which of course is the same as the indicator of st less than b. So this reflected payoff, if you like, in this case actually is a bit simpler than what it was earlier. It's just indicator function of st less than b, but we still have that part there. But remember that we also had well, you may have forgotten, just before we went on the break, we showed that an expectation under Q of this form, where you had an ST there like that, can be rewritten as an expectation under a different probability measure, where the S then gets taken outside. The B can also come outside because it's just a constant. But so if you do that, you have to, it's with the understanding that the measure changes, and now the drift of the log stop price is now plus a half sigma squared, whereas under Q, dxt has a drift of minus a half sigma squared. So under Q, it's a minus. If you're under a Q star, the drift is plus. So we proved that essentially using a PD argument in the last, I think the homework, but just before we had the week break. But I mean, for now, you don't need to remember why that's true, but just you know, just know the result essentially. So it says, yeah, with the understanding that W is a Brownian motion under the measure Q star, then it turns out then, well, so yeah, okay, so we've now written the price of this no touch option as the difference of the price of 2 European type options. This is actually what we call a digital call option payoff, that indicator function, but we've seen how to price such payoffs, and this is as well, except that with the slight quirk that we're operating under a different measure Q star. But both of these are both of these expectations are fairly easy to compute. They're just like the digital calculations that we've done in the past. The only difference, you just need to remember that this one, the stop price and also the log stop price, has a different drift to the S here, where we're working under Q. So this is in the notes somewhere where we price a digital option under the Black. So this would be a digital call option. I mean, some of you might even be able to do this in your head, innit? But when you go through the usual phi calculation, I mean, the quick way to do this is just to assume that you don't have any conditioning here, and do the calculation as usual, and then you look at the final formula, and then you just replace t in the final formula by t minus t, and that works essentially because of the Black-Scholes model is, well, I mean, I think we've done this calculation. It's essentially time homogeneous. So if you do the calculation, if you calculate this expectation without the conditioning there, all you've got to do to make it work with the conditioning is replace t by t minus little t, and replace the initial stop price by whatever the current stop price is s. So that's the easy way to get this formula, but we've done that in the notes anyway. So what I'm saying, I mean, you would start off just by calculating this as Q of st greater than b, and then you would take the log of both sides, or okay, you'd probably divide by S0. You would then take the log of both sides, subtract the drift, do the usual Z thing. So I'm not going to go over the details of that because you've hopefully done that a few times now anyway. But I'm just saying we've essentially done this calculation before, and you would get to this specifically also because there's no drift in this question, so the formula is slightly simpler. And then similarly here, well, there's the additional S here would be there, but otherwise this is a similar type of calculation, except you also have a less than there, so that's why you get a phi C there and a phi there. But also the fact that you've got a minus here instead of a plus, the reason for that is because under Q star the drift of X has changed. But essentially it's just it's the usual thing. You know, S is log normal, but when you take logs, you're back to just a computation involving a normal random variable either exceeding or being less than a barrier, or some level, and then it's just a phi Z type calculation. So when you do that, you end up with this nice formula for the price of this no touch option. So we didn't have any kind of explicit formula, or didn't, but at least in this case, now this is one advantage of when I'm not even sure. If I hadn't set the interest rate to be 0, I'm not sure if any particularly nice formula comes out. Maybe it does, but it would be a lot messier. I'd have to check that in Mathematica or something. So it's one advantage that, you know, it's certainly cleaner to just consider arc 0 for sort of homework questions and stuff. So this is the well I claim is the formula for the price of this no touch option, where TOR is the time to maturity and S is the current stock price, and of course B is the barrier. And there is no strike for this type of option. It's a simpler type of barrier, so it only has a barrier level B, and it just pays 1. Remember, if S does not hit the barrier level at any time over the lifetime of the option, which is capital T. So then, okay. So I forgot this is written. So I've kind of written this as part of the question rather than as part of the answer, but actually you kind of can consider that this is part of the question. But yeah, maybe I should rewrite because this is from last year from another course. But so it says anyway, so verify that the correct boundary and terminal conditions are satisfied by this explicit formula. And then, okay, there's some other stuff that we'll get to. So first of all, we need to verify that along the barrier, this option is worthless. But so in other words, that P, well, yeah, exactly what we see there. If we evaluate P of BT, the answer should come out to be 0, because if you hit the barrier, the option becomes worthless. So if we do that, well, if S is B, then B over S is 1 and natural log of 1 is 0, and similarly here. So this formula simplifies to this if the S here is set equal to B. And you can see you end up with phi C of a half sigma squared TOR divided by that minus phi of that. But probably you know this from the graph of the function, phi C, if Z is greater than 0, which it is here, because this value is a positive thing divided by a positive thing. So phi C of Z for Z greater than 0, yeah, as I said, there is equal to phi of minus Z. It's just something that comes out from the symmetry of the normal distribution. I mean, if I try and draw a normal distribution, but not too bad for me. Yeah, okay. I'm just saying that this area here, if this is Z, actually I'm gonna do a straight line for that if I can. Yeah, it didn't work, didn't it? Okay. Can I not do that? Yeah, that's been it. Yeah, so if this is my Z value and this is my minus Z value, should also be the same distance on the other side, then I'm saying that, yeah, I'm just saying that this area is the same as that area, which I'm sure you all know, but maybe it's not so obvious when you just see the formulas. So I'm just using that property. I'm saying, of course, that this is the standard normal density. But of course, when we integrate that, we get to the phi function. So because of that, this term exactly cancels that term. This does indeed verify that this formula has the correct behavior along the barrier. So to check the terminal boundary condition, well, what's the value of this option at maturity? Well, it should in fact just be the same as a digital call option. Again, I suppose I can draw this a bit nicer with the straight line feature. So at maturity, the behavior should be this. I guess it's an arbitrary convention. Yeah, I think the way I've done it is that, okay, in principle, you've got to say what's the value of the option if S is exactly B. I'm going to use the convention that at B the value is 0 and not 1, but it doesn't actually matter because S is a density, so it won't affect the price. But at maturity, the value of the option is 1 if and only if S is greater than or equal to the barrier. So that's the formula we should get when we look at this formula. But instead of letting S equal to B, rather we let tau tend to 0. Tau is the time to maturity. So if we let the time to maturity tend to 0, what do we get? Well, we know that B is less than it. So I'm assuming now that B is less than it. So I'm assuming that we haven't hit the barrier. So therefore, log of B over S is log B over S is less than 1. So the natural log of it is a negative number. This is becoming insignificant compared to that when tau is small. So it's becoming a negative number. Essentially, it's just a negative number divided by this then. But because the tau is going small, this whole thing, the thing inside the phi c, tends to minus infinity as tau tends to 0. If we look at the other term, then B over S is still negative. This is still really irrelevant when tau is small compared to that. This term swamps this term is tau, so it doesn't really matter whether we have the plus term there or the minus term. It's still the same behavior. So it's essentially in the limit you get phi c minus infinity minus S over B phi infinity minus infinity. Phi c of minus infinity is 1 and phi infinity is 0, because remember phi c of infinity is the probability that a standard normal phi c of minus infinity is the probability that a standard normal is greater than minus infinity, which is of course 1. So the answer comes out to be 1, and that was assuming that B is less than S. It's a good point. Okay, did I actually check the other case? Well, do I care? Sorry, I was just trying. So yeah. So let me think. Should I be considering the final case, which is if S is less than B, or possibly the formula is not actually valid in that case? I mean, it's obvious that if S is less than B, the thing is worthless. So we can basically just say that P of ST is 0 in that case if S is less than B. So there's no, I mean, I don't think if we actually check the formula that if we use the same formula that will actually be true. So we just use the manual override, like of common sense, that if S is less than B, then P of ST, or in fact, if S is less than or equal to B, then P of ST is equal to 0. We did, of course, check that the formula is correct and consistent when S is equal to B. So, okay, so we've already done a fair amount there. Now, so we go back to how this was written. Okay, so I mean, we skipped a few details here, but if you go through this, we did essentially already prove here, if you're happy with going from this to that and similarly from this to that, and as I said, we've gone from that to that already, like, I don't know, quite a few lectures or videos ago, then that is a proof. But in a sense, we're kind of verifying that our calculation is right, doing some common sense checks that this does have the correct behavior along the barrier and at maturity. But actually, if you wanted to convince yourself that this was true without even looking at this, you could say, well, this is the price of a digital option with this payoff, and this is the price of an option with this payoff before we make the measure change. So in fact, both that and that satisfy, although it's not maybe immediately obvious, but from the general theory, both terms here satisfy the Black-Scholes PDE, and therefore their difference satisfies the Black-Scholes PDE because it's a linear PDE. So in fact, that's another way to see that this, I mean, I haven't actually written that here, but another way to see that this is the correct solution, to see that it satisfies, we've already verified it satisfies the correct boundary conditions. But from what we know from the general theory about just the fact that pricing any kind of European type payoff, by that I mean a non-path dependent payoff, i.e. in this case what we're calculating here and also here, this, although exotic, is still a European type payoff. So from the general Black-Scholes theory, we know it satisfies the Black-Scholes PD. So that's another way of thinking about this. If you don't like static hedging, saying that, I suppose you wouldn't have come up with this formula if you didn't know anything about static hedging. Well, then maybe it's another way of doing it, but it's just another way of thinking of it. That's because of what we know about the Black-Scholes PD, and we can manually check the boundary, because that's another way of verifying that this P of ST is correct. But anyway, so I think there was another bit here. It says verify. Oh no, we've done that. What is the sign of the gamma of the option for S large? Explain how you would get. Okay, well, let's do the gamma part. So I think there's a graph here. So this is basically, this is a plot of P of ST. This is the price. Should we have this? So this is S here on this axis. This is the price of this no touch option, which remember pays 1, but only if S never hits B throughout the entire lifetime of the option to the final time, capital T. So as you would expect, if your current stop price, and your current stop price is what I'm plotting, what I have on this axis, is very large, there's a very, very low chance. So think of that, we have the fixed maturity, time to maturity of capital T here, or more generally, say T minus T, because TOR, which you often call it. If S is very large, there is an astronomically low probability that S will actually go and hit the barrier and knock nothing out. So therefore, you're almost guaranteed to get your $1 if S is very large. And remember, we're assuming the interest rate is 0, so we don't have to discount anything. So that's why the option has this behavior tending asymptotically to 1 as S goes large. It's also fairly intuitive, I'd say, that as your stock price increases, it's less and less likely that the stock price will then hit the barrier, because there's no mean reversion or anything with this process. So it's also intuitively fairly obvious that the thing has to be monotonic. So it has to be monotonic, and it also has to be less than 1. So, but you can also see that to stay below this line, the slope of this thing also has to tend to 0. Okay. So the slope of this thing is PS of ST, i.e. the derivative of PST with respect to S, which is what we usually call the delta. But if the slope of this is tending to 0, as you can see from the graph, then the gamma must be tending. Actually, it's not. Okay, how did I explain this here? This can. Okay. So yeah. So okay. This can only happen. For the second part, P of ST tends to 1 as S tends to infinity, since we are almost guaranteed the final payoff of 1 if S is far away from B. That's fine. We've already essentially said that. This can only happen if the slope is decreasing in S. Oh, okay. Sorry. So I was asking about what is the sign of the gamma of the option for. Okay, so all right, so it's slightly different to what I thought I was asking you. So I'm saying that yeah, okay. So the slope of this line, I mean, here it's quite it's not very good, but you can see here the slope is positive and quite strongly positive, whereas here you can see that the slope is tending to 0. So it's quite, the slope around here is quite small. So that if the slope is decreasing, it means that the gamma is negative, because the gamma, remember, is, which we define, remember, as, well, is PSS of ST, but it's also, which is the same as d by ds of PS of ST. So I'm saying if PST is decreasing, which you can obviously see from the graph, then if something is decreasing, its slope has to be negative, assuming it's differentiable. So all I'm saying is that for S large, so I think the key is I'm saying that S is large, so I'll use this notation again, much larger than 1, but not actually infinity, but S less than infinity, then we can see that the gamma is negative. That's the point I'm trying to convey. Gamma is negative. I mean, actually, I think it's negative everywhere in that graph, but it's an easier intuition. It would be harder to prove that the gamma is negative here. I'd have to think about that some more and would probably involve a lengthy calculation. But we can kind of just use our intuition about what's going on here because we know the thing. We know the function is monotonically increasing, but we also know it has to stay below 1, so it can't really do much else than what you're seeing in this graph. It can't, be oscillating around. It can't go above that line. It can't be going, like this or something. Yeah, for the reasons that we've explained. So I should probably bring that back. So was that the end of that question? So half an hour in. Oh, there was a bit more. Yeah, okay, we can say a bit more then. Just grab a drink a second. So was this in the question? It says, yeah, okay. Explain how you would compute the density of the minimum stock price at time t and also the density of the hitting time to b under q in terms of p of st if the current stock price is just equal to s and we assume that s is above b, or else it's not really very interesting. So it says here, yeah, so from the very first lecture, we know that for any random variable x with a density given by f of x, the density is equal to minus d by dx of the complementary distribution function of f, which is this. So in this case, the density of s under bar t, which remember is the minimum stock price over the time interval 0 to t. And remember, this option that we've been considering pays 1 if the minimum stock price, i.e. this, is greater than b. That's what we've been considering. So using this formula in our specific case of interest here, so my dummy variable is not x now, it's capital B, but that's fine. We can choose whatever letter we want. So minus d by db of the probability under q of the minimum stock price being greater than b. Well, q of the minimum stock price being greater, that's precisely the price we've just computed. So that's the same as this expectation, the expectation of this indicator function, which is just d by db of p of st, but we've got a formula for that here. So if you, I mean, I don't think I bothered actually not that formula, our general formula here rather. So if you go away and actually differentiate this formula with respect to b and then multiply by -1, what you will get is the density of hb, which is the time it takes the stock price to hit the barrier b. So let me draw that again. Oh, there it is. Yes. So yeah, that's fine. So if S0 is here, say, so here's our stock price. I'm just saying that HB is just simply, the time here, HB on the time axis at which the stock price eventually hits the level B. Now, a good question is actually, yeah, a natural question to ask. It's maybe not, it's not obvious. It's a very interesting question. How do we know that the stock price will ever hit the level B? Is it possible that it won't? Well, it turns out you can show that it will hit the level B. I may put this as a question for next week, essentially because the log stock price xt, the natural log of st, we know from Ito's lemma, if the interest rate is 0, evolves as minus sigma squared dt plus. Yeah, this might have been that question that I removed because I had to check some technicalities. Yeah, okay, I remember this. Well, yeah, I can basically explain that now. Yeah, so because the interest rate is 0, the log stock price evolves as follows. The STE is that d of xt is minus a half sigma squared t plus sigma dwt. Maybe I have said this, I can't remember, but I'll say it again. So because of this xt, the log stock price drifts to minus infinity, and therefore the st, which is e to the xt, tends to 0. So because st tends to 0, it must hit any level b before that. So essentially that, well, it's a quick kind of back of the envelope proof of that. You probably need a bit more rigor to do that completely properly, but that essentially gives the idea as to why s, tends to 0 as t tends to infinity when the interest rate is 0. So in particular, it must hit the level B. So what I'm saying is that this implies that HB is less than infinity almost surely. And we've just given a way for it to actually compute the density of HB. But then the other thing, the thing we just did, was the density of S bar T. The next part is looking at the density of H bar T. So if you want the density of H bar T, that will be d by dt of this expression. Because we're still using this general formula from the very first lecture, but now our interest is in HB exceeding a level T rather than S under bar exceeding a level B. However, this event, as we said earlier, and this event are the same. So we've already derived a formula for this. The formula for this is just our formula here. So, but now the difference is that we're not going to differentiate in B. We're going to differentiate in T. So if we do that, and again, I haven't actually done the differentiation, but you would just be looking at this and essentially differentiate with respect to Tor, because it doesn't really matter if you different. Well, yeah, depending on how you want to do it and what time you evaluate it, but essentially you'd have to just go. I mean, it'd be a little bit messy because of these extra halves. But if you go away and do that, then you'll get the density of the hitting time to be, which is I don't know. I think there's graphs of these somewhere. They supposed to be. Did I accidentally cut them? Yeah, no, here they are. Yeah. So this, when you do that, this was the density of the minimum stock price, and so what were my parameters? My initial stock price was 1. So why does the density stop here? Why have I not continued, a density that goes like that? Well, because there isn't one. Because of course the minimum stock price has to be less than or equal to the initial stock price, which in this particular numerical example was 1. So that's why there is nothing else there. So that verifies that this qualitatively that my graph seems to make sense. It also, this is still a density, so the integral of this thing, if you went away and checked, is 1. It's a density, but it looks odd because it's kind of got the right half missing, but that's actually correct for this, because of this. Whereas in this graph, we have to specify a time value because it's S under bar T. So I need to know, well, what time are we interested in? But there isn't a B value for this question because, in a sense, B is what's on this axis. We're evaluating the density of this with the dummy variable of B. But in this graph, this is the density of HB. So in this case, you have to fix a B. And then on this axis, the dummy variable would be capital T. So there is no fixed value of capital T for this graph because you don't know when we're going to hit the level of capital B. So this is also a density, but you can see it typically has this quite fat-tailed behavior, similar to, in the video, which hopefully you've seen about the hitting times, where we look at the density of Tor B for brain mesh. It's qualitatively similar to that. It's quite a fat-tailed distribution. So that's the end of it. That's okay. Yeah, I agree. So I guess that stuff is quite hard, but you don't need to perfectly get it now, but you need to obviously hopefully get this stuff by January. I should say I'm writing the real exam at the moment. I wrote it like a few days ago, and Marcus has already sent me the his feedback on it, like 22 points about it, often saying, "Oh, actually, you should simplify this and simplify this." So it is very, in terms of the writing of the real exam, he's very vigilant that the exam is fair and not too difficult. So, I will be writing the second draft of that later today. But anyway, so we have another question now, then, which is a bit different, which is where we look at a time window barrier option, which pays the usual European call option at the final time T, as is usual, if S hits a barrier level B less than this year at any time in this alternate or this different time period 0 to T1, so where T1 is less than T. So it's a usual European option, but you only get the payoff if S, in addition, hits a barrier level which is less than the initial stock price over some time interval which is less than the total time interval, which is earmarked here by the fact that I'm saying that T1 is less than T. So, if we maybe delete this one, isn't it? Yeah, a bit short space here, then yeah, if we redraw this, I'm saying that so I've got a barrier like that, and I've got that time, and then I've got the later time, and I'm saying you've got like T1 is here, and the final time is T here, and we've got a barrier level here, and you've got your initial stop price here, and you've also got your strike price level. So there's a lot to add into this graph. So that would be K, for instance. So I'm saying that to make money, this option has to start like this, hit the barrier there, you can go through it if you want, and then eventually end up above K so that the call option expires in the money, as it were. So I'll just put the K there as well. So that's a typical trajectory that would make money. But if the stock price ends up above K but does not hit the barrier over that time interval 0 to T1, there's my 0 there, then we won't make any money in that case. So it's slightly more interesting than the standard barrier option. And again, I should say I did an internship at HSBC. It's one of those skyscrapers at Canary Wharf, if you've been over that way in London, but you can see it from about 5 miles away. Much of that internship was pricing these kind of barrier options. So they are something that they definitely care about in practice. So what can we say about them? Well, it says write down the PDE with an appropriate boundary condition for the price V of ST of the option under the Black-Scholes model at any time T in the first time period. So I'm assuming T, little t, is somewhere in this time period here, given the current stock price is S. And then it says write down an explicit expression for VS0 as an expectation, and something about replicating the option, but we can get to that. So all the options that we consider for the will always satisfy the Black-Scholes PDE. So that's fine. That's, if you're asked to do that in the exam, that's some easy marks. The hard part is what are the boundary conditions. Well, so the boundary conditions are, well, let's look at this one first. So if S is B, then essentially this option becomes, well, if S hits the barrier, the option becomes a European option, because then the barrier clause has been triggered, and we don't care about barriers going forward. So because of that, the boundary conditions that when S is B, VBT is just CBT, where CBT is the usual price of a Black-Scholes option when the current stock price is S and the time is T. So that's what's going on there. But there's also the scenario of, I'm just going to have to draw everything again now. So what about, okay. Yeah, well, okay, I need to put my barrier level in there, and that time and that time. Yeah, okay. So we've said now what happens to, what we've done tells us what the value of the option is on this line here. That's what we've just done here, and we've said that on this line here, the value of the option would in fact just be the value of a standard European call option with a stop price equal to B, with the stop price equal to B. But then I need to also say something about, well, what about the barrier, the value of the option along this vertical line here? So in that case, well, along this line here, this part, the option, so the way it works with these barriers is that you have to say, well, what is the option worth here if you were just giving it new? So it's not relevant how you got there. The understanding is with the boundaries is that you're just being given the option, like as a Christmas present right now, today. Is it worth anything? Well, it's not worth anything on this line because it's got no time to knock in and hit the barrier. Or it's not worth anything above this line, above the barrier level B, which of course is this level here. So along this line, the option is worthless. Below that line, the option is worth the usual European payoff, and therefore we can write the value as that. So, however, so we've specified what the value of this option is. I'm only concentrating in this question of what the value is from 0 to T1 because it's kind of boring after T1, because either the thing has died or it's just become a European option. So either of those scenarios are quite boring to us. So what we really care about is a PDE for the value of the option in this area here. But it turns out, yeah, for these PD example, it's sufficient to specify the boundary conditions for the rectangle just along the edges of the rectangle. So actually, I don't even need to specify. I can actually just say that I can essentially just say that V of ST is equal to 0, i.e. it's 0 along this line here, because what it's doing down here is irrelevant, because all that, yeah, it's sufficient to, once you specify the behavior along there and along there, that's sufficient to uniquely determine the solution to the PD. I'm not actually proving that. That would be a difficult thing to prove, but it's true. So all that actually matters as far as the boundary conditions is that along this barrier, the value is just equal to the Black-Scholes value, and along this barrier, the value of the time in the barrier is worthless. Because if you're above B, you've got no time to hit the barrier because you're already at T1, is the way to think about it. So the final part was just how would you replicate this option? The value of the option at time 0 is just the usual discounted value of the expected payoff under Q. So what is the expected payoff? Well, it's the usual European call option payoff, but with the indicator function. So what is the payoff? Well, we need the minimum stock price at T1 to be less than or equal to B. So it's the opposite of the previous example with the notice. We need the minimum stock price at T1 to be less than or equal to B, i.e. we need S to hit the barrier, or else this thing is going to die. And I've reminded you what the definition of S under bar T is. So the bar, but under S rather than above it. So to replicate the time in the barrier with dynamic trading in the usual way, as in the lecture notes, you start with this amount of cash as usual. And it's just otherwise it's just the same rule. You hold V of ST, you hold the delta, you take the value of the option, you partially differentiate with the evaluated ST, and that's your delta. And we've seen the PDA. Now, no, I haven't actually solved this PDA. To actually solve it, you'd need to go away. Well, that was the kind of thing I was doing in that internship. I mean, you could use either a Crank-Nicholson or finite difference scheme, or I think you could do it by using sort of convolutions of PDFs of the density of S at two different times, T and T1, but we're not going to get into that today. But so you would have to have a way of solving this PDA, and you could do it. It's just a bit too messy for this question. But once you've done that, then that gives you your delta. So essentially, the same method applies, that you solve your PDE and compute the delta, and that's how much stock you need to hold at each time, with the usual proviso that you have to keep the remaining stock not under your bed but in the bank account. So this is still the usual self-financing equation, where this is how much you hold in the stock at each time, and this is how much you hold in the bank account, or rather this is how much you stock, your total wealth minus how much you've got tied up in the stock. But what happens? But if S, okay, so what does it say? If S is not hit B by T1, then the option becomes worthless. So in this case, the V of ST1 T is equal to 0. So in that case, you've successfully replicated the time window barrier option, and no further dynamic trading is required. Conversely, if S does hit B, then V of ST just becomes the usual C of ST, the usual Black-Scholes option formula for a call option, and you just continue dynamic trading in the usual way with the usual delta formula, for which we have an explicit formula, remember, in the notes. So I'm saying it will just be CS of ST, T, for which there is a formula in the notes, i.e. the usual Black-Scholes delta formula. Because as it says here, in this case, the timing about has become a standard call option. I mean, I should say that, I mean, if S hits B, then of course it becomes a European, if S hits B before T1, it becomes a European call option immediately. So actually, this will be true immediately. It may not be completely clear from what I've said there that that's true. So otherwise, that's the end of the question. Let me just check the chat because it's on a different device. Can't I see this? Sorry, I don't seem to be able to see the chat here, but I'll try and bring it up now. Join Teams meeting. Opening Teams now. So I don't know if okay, showing conversation. Okay, there's a few. So why? So yeah, sorry, I'm only seeing this now. Why in this question is not the same with Q1 ST greater than B? Why in this question? Question 1 was not a time window barrier; it was just a standard barrier option. So there were 2 different maturities, and also question 1. You got your payoff if you didn't hit the barrier. In question 2, you have to hit the barrier to get a non-zero payoff. So they kind of, in some sense, they're the opposite of each other. But also, question 2 is more involved in the sense that you've got this additional maturity T1 as well, which is also why I haven't actually given an explicit formula for this P, because that would be rather complicated. Maybe we'll do something like that later in the course. But even if we did, it would be like a few integrals or something. But any other questions?
Hi, Professor. Can you move to the question 1?
To question 1?
Yeah.
Yeah. So I'm just increasing the volume so I can hear you. Yeah.
I think the formula, the first bracket of the formula is minus sign of half sigma square tau PST.
You mean here?
Down. Move down a bit. Next line. PST1.
Here?
Yeah. It should be minus sign.
So
because I think it has same process to standardize normal.
I mean, we're working on for that probability. So it's good that we're checking it. We're working under Q. Under Q, dxt has a drift of minus a half sigma squared when the interest rate is 0. Gosh, there's just no room for that here. dxt is minus half sigma squared dt plus sigma dwt. So I think the reason it's positive is because the drift, you subtract the drift, but the drift is negative, so it's a minus times a minus. But there may not be much room to do this, but as I said, essentially you can just do the calculation P of ST. You can just do the calculation at time 0, and then you can easily adjust the final answer. So what we need to calculate is P of ST being greater than B. Let's then divide both sides by S0. Or unless you're happy with that, but I think that's right. Then you would, then you
because would, I think they have same process to they.
So what has the same process?
The standardized normal process.
I mean, there is no standardized normal process. There's no such thing. Yeah. So I think you need to be, there's only one process we care about, which is this XT process. The standardized normal is a distribution, but it's not a process. So
okay. Can you move down a bit?
Yeah.
I also wonder how you get minus infinity of the composite phi.
Do you mean here?
Yeah.
Yeah, because B is less than S. So therefore B over S is less than 1, and therefore the natural log of B over S is less than 0. Maybe it wasn't clear immediately if that makes sense. And therefore you've got something negative here divided by something which is tending to 0. So therefore it's something that tends to minus infinity. And this term is basically irrelevant because it goes very small, whereas this does not go small. So this term becomes irrelevant compared to that term.
Oh, thank you.
And this term is essentially the same because it doesn't matter whether this small term is positive or negative. It's not affecting the outcome. This term would be significant. In fact, a nice thing to do, you could go away and see what happens to this formula when tau goes large, tends to infinity rather than tends to 0. I've probably done that in the past and I've probably forgotten what the answer is. So that's something you could do as practice. So, And any other questions? Yeah. But that's good that yes, that you're questioning such things. Yeah, you know, you have to question things to learn. You know? Okay. So, well, any other questions or? Okay. Well, yeah. So I know that stuff's probably a bit scarier. As I said, that there hopefully won't be too much more new material on the course. I will try and make it that in the last 2 weeks it will just be doing mock exams. So maybe there might be a little bit of new material next week. But yeah, Marcus is also very keen that I don't give you too much stuff to do. But so I will end this recording here. I will upload both the videos from today on Keats, although maybe I don't know, maybe you access them, or I think you can access them anyway from the chat, I think, can't you? But and feel free to send me an email. Email is better than Teams if you're still confused about anything or have any other general questions. So I will end the recording there, and again, thanks for attending.